In this example, we're going to carry out a hypothesis test for a proportion. So our scenario is that a chip manufacturer claims that at most 2% of their chips are defective. We've tested a sample of 400 chips and found 3% of them to be defective. Does that, at the 0.05 significance level, disprove the manufacturer's claim that no more than 2% would be defective? So this is a test concerning a proportion. We're going to begin by stating our hypotheses. A null hypothesis will be that the proportion is 2%, as the manufacturer claimed. That's the manufacturer's claim. Or we could write it as less than or equal to. Our alternative, our suspicion, is that the true proportion is greater than 0.02. Okay, and so null hypothesis, assume the proportion is 0.2. Alternative, right-tailed test, greater than 0.2. So we're going to compute a test statistic, and the test statistic will be z equals p hat minus p, all divided by the square root of p times 1 minus p over n. So p hat is the sample proportion. P is the value from the null hypothesis, 0.02 in this case, and of course n is the sample size. So our p hat is from the sample. That's our 0.03 observed in our sample. P is the 0.02 from the null hypothesis. And n is our sample size, in this case 400. All of that goes under our radical sign. So now we just can use any calculator to compute that test statistic. It will be a z-score. I'm going to go ahead and use Excel as our calculator. So our observed sample proportion was 0.03. The population proportion is the 0.02 that we assume to be the true population proportion according to the null hypothesis. Our sample size was 400. And now based on those values, we compute our test statistic. So I'm just going to do the computation here, beginning with an equal sign. Parentheses for the numerator, it'll take the form p hat minus p, sample proportion minus population proportion, B1 minus B2 are the cells in question. Close the parentheses around the numerator, divide by the square root SQRT, parentheses, and then it's going to be p times 1 minus p. This is p from the null hypothesis, 0.02, times, in parentheses, 1 minus p. Still clicking on p again. That divided by the sample size n all fits inside that square root, which is in the denominator. So altogether, we've got equals b1 minus b2 in the numerator and square root of b2 times the quantity 1 minus b2 over b3 in the denominator, noting a set of parentheses grouping up those two terms in the numerator, noting that those parentheses for the square root function encompasses that entire product, b2 times 1 minus b2 over b3. So we'll evaluate that and we get a test statistic, which is really a z-score, right? So that's our z-score. We're going to use the normal distribution function to calculate an area. It will always give us area to the left. So we type equals. The function is norm.dist, and we give it the test statistic as our input, mean 0, standard deviation 1, and the option true. So when I use this norm dist function to get an area corresponding to a z-score, all I have to do is give it the z-score, comma 0, comma 1, comma true. 0 and 1 correspond to the mean and standard deviation of the standard normal C distribution. So let's see what our area to the left is. We get 0.92344. Because this is a right-tailed test, we're going to want to get our p-value by subtracting that from 1, because we really wanted the area to the right, so we type equals 1 minus that computed area to the left, and that will be our p-value. So it looks like our p-value is about 0.07656. Okay, that's more decimal places than we really need, but it's fine. So what have we got? We've got a test statistic, which was 1.43. I want to think about on our normal distribution there where that puts us. Not quite 1.5 standard deviations above the mean. And we, because of our alternative hypothesis, right, we're looking at a right-tailed test, and we are computing, essentially wanting to know the probability that we would have observed a proportion, a sample proportion that high or higher if the true sample proportion was 0.02 as indicated in the null hypothesis. So by using that norm dist function, what we determined was that area to the left was 0.92344, which means the area to the right is 1 minus 0.92344, which we computed 0.07656. That's our p-value. At the 0.05 significance level, alpha is 0.05. We now look at our p-value, and we want to know, is our p-value greater than or less than our alpha? In this case, we see our p-value is bigger than alpha, and when the p-value is bigger than alpha, we do not reject the null hypothesis. So at the 0.05 level, we do not have sufficient evidence there to prove that they have more than 2% of their chips defective.